Okay, so let's start with this. Let's start with the next topic, which is momentum. Now, this is a fairly small topic. There is not much in it in terms of concepts. So we should be able to do the concepts in just 15-20 minutes in the beginning of today's class. So let's start with this momentum and try to understand what this concept is. So in our syllabus, we only have linear momentum. Okay. So those of you who have done physics as well, you might have done other types of momentum as well, in which maybe there were some collisions at some angles. Here, the collision is always going to be head on, as in there's going to be no angle involved as such. The particles are going to be moving in a straight line. All right. So it's pretty straightforward because of that. It's only linear momentum. All right. Now, how is momentum defined? Let's try to understand that let's try to understand momentum, the concept of momentum, first of all, using this example. Let's say we have these three people and they're running like this, right? So you have three people, they have different masses. Mass of the first person is 70 kilograms and is running at 4 meters per second. We have another person two, he's running at 7 meters per second to the left side. And we have another person three, he's running at he's also running at 7 meters per second, but his mass is 95 kilograms. Now think about it. Let's compare the first two people, person one and person two. Person one has a mass of 70 kilograms. Person two has a mass of 70 kilograms as well. So both of them have the same mass, but they're running at different speeds. One is running at 4 meters per second and the other is running at 7 meters per second. Which one of them do you think is going to have higher momentum? Which one of them is going to have which one of them is going to be difficult to stop? More difficult to stop, the first one or the second one? Both of them have the same mass, but the first is running at 4 meters per second and the second is running at 7 meters per second. Who do you think, if you were to try and stop them, who will be easier to stop and who will be more difficult to stop? Anyone?
So the first one will be easier to stop.
The first one will be easier to stop, right? Why? Because he's running slower. This one is running faster. He's going to be more difficult to stop. So we basically say the first one has less momentum as compared to the second one. So basically, the person who has a greater speed or a greater velocity, that person has more momentum. All right. So one thing that momentum depends on is velocity of a person, velocity of an object. But then if you compare the second person and the third person, both of them are running at the same speed. However, the third person is heavier. He has more weight. He has more mass. He's 95 kilograms and person two has a mass of 70 kilograms. Which one of these two is going to be harder to stop? Person three is going to be harder to stop, right? He has more mass. If he is running at the same speed, at the same velocity, as compared to person two, the person that has more mass, that's going to be more difficult to stop. So think about something very large moving at a certain speed as compared to something very small moving at that same speed. Stopping that small object is going to be easier as compared to stopping a very large object. Okay. So basically, there are two things that momentum depends on. So in this case as well, we can say person three has a greater momentum as compared to person two. Now, how do we quantify this? So logically, we understand, okay, a greater velocity means greater momentum. A greater mass means greater momentum as well. So basically, momentum is defined like this. This is the formula that we've got for momentum. Momentum depends on two things, and that it's equal to mass into velocity. Momentum is equal to mass into velocity. Now, in the last topic that we did, work, energy, power, all the three quantities that we did, they were scalar quantities. All right. But now, momentum this is actually a vector quantity. It's a vector quantity, which means that the direction of momentum is also relevant. Direction also matters. And since it's a vector quantity, if you define one direction as positive and another direction as negative, momentum can also be negative sometimes. All right, depending on which direction is taken positive. Just like velocity can be negative, displacement can be negative, acceleration can be negative. Since momentum is also a vector quantity, this could also have a negative value sometimes. So it's a vector quantity. What's the unit for momentum? What's the unit for mass? The unit for mass is kilograms. What's the unit for velocity? Unit for velocity is meter per second. So the unit for momentum is kg meter per second. That's the unit that we got for momentum. Okay. So this is the formula. Momentum equals mass into velocity. We can write this in short form like this. Rho equals mass into velocity. Now, mass is represented by this letter m. Velocity is represented by this letter v. Now, since we are already using m for mass, we can't use the same letter for momentum. So we use a different letter. This is called rho. This is a Greek letter called rho. It looks very similar to p. We can also just write p instead of rho. That's perfectly okay. But it's actually supposed to be rho, and it's written like this in this form. Very similar to p. Okay. This is the notation that we use for momentum. This is the formula that we have now. Rho equals mv, momentum equals mass into velocity. Okay, that's how momentum is defined. It depends on two things, mass and velocity. Now that we know the definition of momentum, now we can quantify the momentum of these three people, right? All of them had a different momentum. Can we find the magnitude of the momentum now, the value of the momentum now? Now, since momentum is a vector quantity, we would need to define one direction as positive. So let's say the left direction is positive here. Since they're both all moving in the left direction, so we say the left direction is positive. Now, what's the momentum of the first person? Mass into velocity. Mass is 70, velocity is 4. The momentum turns out to be 280 kilograms meter per second. For the second person, what would this be? Mass is 70, velocity is 7. So for the second person, this is 490 kilograms meter per second. And then for the last person, we have 95 multiplied by 7. What does that give us? 7 into 100 is 700 minus 35, that's 665 kg meter per second. So you can see the momentums of all of these different people. For the first person has the least momentum, the second one has slightly greater than that, and the third one has even greater momentum than the second one. So these are the values, and that's what we understood logically as well. But this is how we quantify those momentums now. So now we can write down what the exact magnitude of that momentum is. All right. So that's the first thing we need to know about in momentum. Rho equals mv. Okay. Now the second thing is conservation of momentum. So now that you understand the definition of momentum, now there's another concept, and that is the concept of conservation of momentum. And that basically means that the total momentum of objects, it remains conserved. When does it remain conserved? Whenever there is a collision, the momentum before collision and the momentum after collision, that always remains conserved. That's what conservation of momentum means. Now, the situations that you would get in momentum problems would be that there will be some objects, they'll be moving in different directions, and there will be some collision. So one object will be colliding with another, then the second might be colliding with another one. So there will be collisions happening. And when those collisions happen, you would have to use conservation of momentum. And what does conservation of momentum say? Whenever there is a collision, the total momentum of the objects in the system before collision, that is equal to the total momentum of all objects in the system after collision. So the total momentum in a system that always remains conserved in case of collision, before and after collision, the momentum remains the same. Now, in short form, we could write it like this. We could say momentum before collision, that remains equal to the total momentum after collision. Okay? The total momentum before collision, that remains the same as the total momentum after collision. Now, let's take an example of this. Let's say we have a horizontal surface like this. And on this horizontal surface, we've got a couple of balls like this. So there's one ball here. Let's say it's called A. There's another ball here. It's B. Okay. Now A and B are moving. Let's say A is moving to the right side at a certain speed. Let's say A is moving to the right at a speed of maybe 6 meters per second. And B is moving to the left at a speed of, let's say, 2 meters per second. We have their masses given as well. Let's say the mass of A is maybe 8 kilograms and mass of B is, let's say, 10 kilograms. These are the two objects that we have. A is moving to the right side, B is moving to the left side. The surface is smooth. The surface is smooth. What that means is there's no friction. If there's no friction, whatever velocity that they're moving at, that remains the same. That does not change, right? So the velocity of the two objects, that remains the same. That there's no deceleration. All right. They're moving like this. A is moving to the right, B is moving to the left. And now let's say at some point they collide with each other. So there's some collision, right? So they're going to collide at some point. So that point is here. This is A and this is B. They end up colliding. Now, once they collide, after collision, let's say we know their velocities after collision like this. Let me actually summarize that information like this. So we have some information about before collision. Before collision, we know that the velocity of A is 6 meters per second to the right. And the velocity of B is 2 meters per second to the left. Now, what about after collision? After collision, let's say you're given that after this collision happens, A starts moving to the right at a speed of 3 meters per second. Okay. A starts moving to the right at a speed of 3 meters per second. Let's calculate this if it's even possible. 6 is 48, 48, and 28, 28. Yeah, okay. So what happens is, before collision, A is moving at 6 meters per second to the right, and B is moving at 2 meters per second to the left. After collision, what happens is, A continues to move in the right direction. So A hits B, and it continues to move in the right direction. And it starts moving at a speed of 3 meters per second. What we need to do is, we need to find the velocity of B after collision. Okay, so that's what's happening, right? We know their masses before collision. We know their velocities before collision. We know the velocity of A after collision as well. We need to find the velocity of B after collision. How do you find that? You find this by using conservation of momentum. Now, what does conservation of momentum say? Conservation of momentum basically says that the total momentum before collision, that should remain the same as the total momentum after collision. Now, what's the total momentum before collision? Remember, how is momentum defined? Mass into velocity. What's the momentum of A before collision? Now, while you do momentum problems, you need to make sure that you clearly have in your head a positive direction, right? Because it's a vector quantity, so you need to be very careful about the positive and negative signs. You have to consider one direction positive. Now, here it's important. Remember, in kinematics, if you had multiple objects, you could take different directions as positive. Here, you are not going to take different directions as positive for different objects. The same direction will remain positive. Now, I'll explain that in a bit more detail in a few minutes. Let's actually do this. Let's consider the right side positive for both objects, right? So let's say we have assumed the right side to be positive for both the objects, object A and object B. Now, what's the momentum of A before collision? Mass into velocity. Mass is 8. Velocity is 6. Plus momentum of B before collision. What's that? Mass is 10 kilograms. What about velocity? Velocity is going to be -2. We are considering right side positive. B is moving to the left side. So the velocity has to be -2 here. Okay. And then what about momentum after collision? This was the momentum of A before collision. This was the momentum of B before collision. Now, what's the momentum of A after collision? Mass of A, which is 8, into velocity of A, that's 3, plus momentum of B after collision. What would that be? Mass of B, that is 10, into velocity of B, that's VB. Now, we do not know. In fact, we know. So let's actually leave it like this: 10 into VB. This is the momentum before collision and momentum after collision. We just equate both of them. All right. And now we can use this to find the value of the velocity.
Sir, your mic's not working.
That equals 24 plus 10 times VB. And that gives you 28 minus 24, that's 4. 4 equals 10 VB. And VB turns out to be 0.4 meters per second. What does that mean? B is moving at a speed of 0.4 meters per second to the right side after collision. That is what happens to this to B after collision. That's the speed of B, or the velocity of B after collision, and it's moving to the right side. Does that make sense? That's how we use conservation of momentum to find any unknowns like this. You might have a velocity missing or a mass missing. You just say, whenever there's a collision, the momentum remains conserved. The total momentum before collision and the total momentum after collision, that always remains the same. Any problem with this?
No, sir.
Any question? No? Now remember, in kinematics, we looked at problems like these when we talked about different multiple objects. Yeah, so for example, this question. There was this question in which a particle was projected upwards from ground, and there was another particle that was released from the top. In kinematics, we looked at problems like these. Now, A started from the bottom and it was moving upwards. B started from the top and it was moving downwards. What we used to do was, we used to take whichever direction the particle was moving in as positive, right? So for A in this case, for instance, since A was moving upwards, A was projected upwards, we took upwards direction as positive for A. And for B, since that was moving downwards, we took the downward direction as positive for B. In kinematics, we could use different directions as positive for different objects. The reason for that was, we were making separate equations for them. We were having a separate equation for this. We're having a separate equation for this. So we could take different directions as positive for both of them. But when we talk about momentum, we have to input all of these values in this one equation, conservation of momentum. Now, in this case, you have to remain consistent throughout, right? It's one single equation in which all the objects are considered. If you're considering one direction as positive for one object, it has to be the same for all objects in the system. You can't take different directions as positive. Okay, so for A, if you're taking right positive, it has to be right positive for B as well. In case you're applying conservation of momentum, here that is going to be important. Now, it's going to be even important to remember when in some questions, you have to use both kinematics concepts and momentum concepts. And you would realize there, when you're applying kinematics concept, you would often be using different directions as positive. And when you're applying conservation of momentum, in that case, you would have to use the same direction as positive for both the objects. So this is something that's important to remember. Okay. Now let me write that down here. When applying conservation of momentum, always take one direction or the same direction as positive for all the objects in the system. Okay, so for all the objects in the system, you have to take the same direction as positive. So whenever you have conservation of momentum being used, the same direction should be taken as positive for all the objects. Okay, that is important to remember. In kinematics, you could take different directions positive. In conservation of momentum, you can't do that. Any quick questions on this?
No, sir.
No? So we talked about the momentum formula. Momentum equals mass into velocity. We talked about conservation of momentum, total momentum before collision, that equals total momentum after collision. And we looked at an example of this, and we looked at how we should take the same direction as positive for all the objects in the system. And that completes the topic. In terms of concepts, this is all that you need to know about. Okay? That's momentum done. Now, if you look at questions, sometimes they're slightly tricky. The momentum part is almost always going to be quite straightforward. What happens is, since it's a pretty small topic in terms of concepts, it mostly comes along with other topics, right? So you'll have a work energy power question in which you'll have a couple of parts on momentum. You'll have a kinematics question in which you might have a couple of parts on momentum, or you might have a momentum question in which you have a few parts in kinematics as well. It always comes in together with some other topic, mostly with kinematics and work energy power. So some parts will be related to momentum, some parts will be related to either kinematics or work energy power. Now, since it's related, it's coming together with the other topics. Sometimes when it's combined with that other topic, that is what makes it slightly more complicated. So you might have a question in which there are two particles moving towards each other, and you have to find the velocities at the point of collision using kinematics. And then for collision, you have to use momentum. And then for after collision, you have to use kinematics again. So things like that. But as far as momentum is concerned, this is all that you need to know about. All right. Now let's have a look at a couple of questions from the worksheet quickly. And then you will do some more practice for tomorrow. And that will wrap this topic up for us. Okay. Let's actually just do one question for today. I'm going to keep this short today so that you have time for practice now. So you should try these questions yourself. I'm going to do a relatively straightforward one for now. And then you will let me know which questions you have problems in, and we will discuss them tomorrow and next week. So the next couple of classes are just going to be on practice questions now. And then if you have more questions, we could have maybe another extra class after that. So you can practice, let me know whatever questions you have. We will, inshallah, discuss them. Okay, so let's start with a simple one. This is question number 1 from the worksheet. Question number 1 from the worksheet. Fairly straightforward. Let's see how we would approach this one. Okay, so it says 3 small smooth spheres A, B, and C of equal radii and of masses 4 kg, 2 kg, and 3 kg respectively lie in that order in a straight line on a smooth horizontal plane. Initially, B and C are at rest, and A is moving towards B with speed 6 meters per second. After the collision with B, sphere A continues to move in the same direction, but with speed 2 meters per second. Find the speed of B after this collision. Okay, now, whenever in mechanics questions, you do not have a diagram given, it's always helpful to draw a rough sketch to try to understand that situation better. So you basically have 3 spheres, and they're placed on a smooth horizontal plane. So let's say you have this horizontal plane, and you have 3 spheres like this. You have one here. And there are a couple of more like this. They're placed on this plane like this. There's one here maybe. And then there's another one here. Let's call them A, B, and C. Now, since it's a smooth plane and the spheres are also smooth, that means there's no friction. If there's no friction, whatever velocities they are moving at, that velocity is the velocities are not going to change while they move, right? Because there's no deceleration as such. Okay, so unless there's a collision that happens, they're going to keep moving at the same velocity. Now, what are the masses that we're given? We're given that A has a mass of 4 kilograms, B has a mass of 2 kilograms, and C has a mass of 3 kilograms. We have their masses given. Initially, B and C are at rest. So B and C, both of them are at rest. The velocity of B is 0. The velocity of C is also 0. And A is moving towards B at a speed of 6 meters per second. So A is moving towards B. A is moving to the right, like this. Now, this is what's happening before collision. What about after collision? So what happens is after the collision with B, so we are talking about collision between A and B. So for now, we are only concerned about A and B, right? C is lying there at rest. We can just ignore that. There's no collision with C happening in the first part. The collision is just between A and B right now. So let's just focus on A and B for now. Okay, so just focusing on A and B for now. C is just lying there as it is. Now for A and B, when A and B collide, we are given that A continues to move in the same direction, but with speed 2 meters per second. So after this collision happens, the velocity of B is 2 meters per second to the right side. In the first part, we need to find the speed of B after this collision. So what's VB? That is what we want to find out. Okay. Now C was at rest before collision. It also remains at rest after this collision because C is not even involved in this collision. So we can just ignore that. How do you find the speed of B? All you have to do is equate the momentum before collision to momentum after collision. So momentum before collision, that should equal momentum after collision. What does that give us? Momentum before collision, momentum of A, 4 is the mass into velocity, that's 6. Remember, we have to take one direction as positive. Let's take right as positive. 4 into 6 plus momentum of B, mass is 2, but velocity is 0 because it was at rest. What about after collision? Mass of A is 4, velocity of A is 2, 4 into 2 plus mass of B, which is 2, into velocity of B, that's VB. We can find the value of VB from this. That's 24 equal to 8 plus 2 times VB. And VB equals 16 over 2. That's 8 meters per second. That's the speed of B after this first collision. That is what we were looking for. Okay, so we just applied conservation of momentum, and we found the speed of B after this first collision. Okay. Now it says the sphere B collides with C now. So now B collides with C. In this collision, these two spheres coalesce. Okay, now this is a word that you will see coming up again and again in momentum problems. Coalesce basically means they merge, they combine, they merge to form a single object. Okay, so they are kind of stick together now after this point. Okay, coalesce means they merge and become a single object. So B collides with C. After that first collision has happened, B now collides with C, and the two spheres coalesce to form an object B. Find the speed of D after this collision. Okay, now after that first collision, now again we have that smooth surface. And you have those three spheres on the surface like this. The masses are given. Now, when the first collision had already happened, what is the situation? What's the state of the particles after that collision? So before the second collision now, what's the situation? Now, at this point, the first collision has already happened, right? A and B have collided with each other. C was at rest after that first collision. B is moving at 8 meters per second to the right. And A is moving at 2 meters per second to the right. So before this second collision now, this is how the three particles look like. A is moving to the right at 2 meters per second, B is moving to the right at 8, and C is at rest. Now the collision is between B and C. Now B and C collide, and they become one single object, D now. Now this is the state before collision. Now we are only going to focus on B and C. Ignore A now because that's not involved in any collision. What happens with B and C? They coalesce to form one single object. So now we have one single object after a collision. A does not change. It's still moving at 2 meters per second. Again, we're ignoring that. We don't necessarily have to show that even. We can just ignore that. B and C merge to form one single object. And we need to find the speed of this one single object. Again, what do? We say momentum before collision. That should remain the same as the momentum after collision. What's the momentum before collision? Mass of B is 2 into velocity of B, that's 8. We're taking the right side as positive, so that's 2 times 8, plus mass of B, which is 3, into velocity of mass of C, sorry, that's 3, into velocity of C, that's 0, equals momentum after collision. Now, what about the mass of D? D is made by merging B and C together, right? What's the mass of B? 2 kilograms. What's the mass of C? 3 kilograms. So mass of D, therefore, is going to be the sum of those two, 5 kilograms. So mass of D, 5 into velocity of D. That is the momentum of D after collision. And now we just solve this. That gives us 16 equal to 5 times VD. And VD turns out to be 16 over 5. That's going to be 3.2 meters per second. That's the speed of D after this collision. Make sense? Any problem with this?
No, sir.
No? So that's the speed of d now. Now it says show that the total loss of kinetic energy in the system due to the two collisions is 38.4 joules. Total loss of kinetic energy. So basically change in kinetic energy, you have to find what was the kinetic energy of the system initially, what was the kinetic energy at the end. How do you find that? Let's try that. Again, we consider the initial situation. Just copy all of this like this. This is what the situation was in the very beginning, right? At the start, this was the state of the three particles. Right? This is what the three particles looked like in the beginning. So this is, you can say, the initial state. Now, what happens at the very end? When both the collisions have happened, what happens after? What happens at that point? At the end, A was moving to the right at 2 meters per second. At the end, A is moving to the right at 2 meters per second. B and C have merged to form a single object, D, which has a mass of 5 kilograms. D is moving to the right at 3.2 meters per second. This is the state at the end. Okay. Now, remember the velocity of D was coming out to be positive. That's why we are saying it's moving to the right. If it was negative, that would mean it's moving to the left, all right, because the right side is taken as positive. In this case, it was positive, so it's actually moving to the right. This is the state after both the collisions have happened, all right. Now, can we find the initial kinetic energy and the final kinetic energy using this? Right? We can find the kinetic energy in the very beginning and at the very end. What's that going to be? Let's find the initial kinetic energy. What's the formula for kinetic energy? It's half mv squared. You have three objects. What about the kinetic energy of A? It's going to be half into m, which is 4. M into v squared, that's 6 squared, plus kinetic energy of the other two objects. They are both going to be 0. You can see what that turns out to be. 2 into 36, that's 72 joules. This is the initial kinetic energy. Then what about the final kinetic energy? What happens at the very end? At the end, what's the kinetic energy of A? Remember what the mass of A was? Mass of A was 4 kilograms. Kinetic energy of A is half into mass, which is 4 into 2 squared, plus kinetic energy of B and C. There are no B and C anymore. There's only D. What's the kinetic energy of D? It's half into 5 into speed, which is 3.2 squared. And that's going to give you the final kinetic energy. What's that? Anybody tell me what that value is? Final kinetic energy. Okay, so this turns out to be
So 33.6.
33.6 joules. This is the final kinetic energy. All right. Now, what's the change in kinetic energy? If you had to find change, for change, you normally do final minus initial. So that will be 33.6 minus 72. The change turns out to be minus 38.4 joules. That's the change. But the question basically asked you for the loss in kinetic energy. Now, the word loss already incorporates the negative sign. So you would say the loss in kinetic energy, therefore, that is equal to 38.4 joules. That's the loss in kinetic energy. And that's what you were looking for. That's the loss in kinetic energy, 38.4 joules. You had to prove that. Okay. So a lot of times momentum questions are just straightforward like this, but sometimes they are trickier. And you'll find that when you do some practice, try some questions from the worksheet now. We will discuss the problems that you have tomorrow and next week then, inshallah. All right. So I'll be uploading this worksheet. I'll actually do that right now so it doesn't get delayed. You can start working on that and let me know the problems that you have. Any problems, anyone? Any questions before we end today?
No, sir.
No? Okay. So now please try those questions and we will discuss them tomorrow. That's it for today. We're done with all the concepts in mechanics. It's just about some more practice now. We'll spend the next few sessions on more practice. I've uploaded the worksheet now. You can start working on that. All right. Allah Hafiz, everyone.